polynomial functions. We're going to look just a little bit more at what is a polynomial and then how do you graph a polynomial without using the calculator. So first of all, a polynomial, this is a very mathematical definition right here of what a polynomial looks like. The A's, the AN thing, AN minus 1, AN minus 2, and it keeps going down until you get to A1, A0. Those just stand for some kind of constant, some kind of coefficient that's in front of each of these x terms. And then your x's, right, you're going to have an x to a power, and you can have that potentially all the way down to just an x, or even not an x, like just a constant term added to it. Okay? N is the highest power in this. Okay, so this one's in standard form where it's actually in order. Sometimes they're not. N is the biggest exponent, the highest exponent. That's considered the degree of the polynomial. Okay, notice that n is an integer. Okay, remember that means not a fraction or decimal, and that it has to be greater than or equal to 0. Okay, so you can't have any negative exponents. Okay, but you can have an x to the 0 power, which actually means that there's not an x term. Okay. So we've kind of done this before with mainly with linear functions, but these are all polynomials. So first of all, you're supposed to decide just, is it a polynomial, yes or no? Okay, so looking here at question 1, are the x's, right, do the x's have exponents? Are they whole numbers? Are they non-negative? Then this is yes, it is a polynomial. It says, if it is a polynomial, what is the degree? Remember, the degree is the highest exponent. So my highest exponent here is an x to the 4th. So this has a degree of 4. And then number of terms really isn't that important most of the time, but in this case, this has 1, 2, 3 terms. Okay, question number 2. Is this a polynomial? Okay, well, looking at this right here, x to the square root power, and we haven't really talked about this yet this year, but that's the same thing as x to the 1/2 power. Okay, well, remember your exponents have to be integers, so no, this is not a polynomial. It's actually a square root function, and that's all I'm going to do because I'm kind of lazy. Okay. Question number 3, again, looking at your exponents, this one has an x to the negative 4. So also no, it's not a polynomial. And technically a negative exponent means that it should be in the denominator. So this should really be written like this, x to the 4th. So this is technically a rational function. I should have put my x here because now it bothers me. Okay, same thing with question number 4. X in the denominator is not possible. This is not a polynomial. It is, again, a rational function where you have x in the denominator. Question number 5, a little bit different. Notice the x is in the numerator, the numbers in the denominator. It didn't say anything up here about the fact that your a's had to be integers. Okay, so this 3 on the bottom, that really means just your a is a 1/3. So this is, yes, it is a polynomial. The degree is the power of the highest exponent. Okay, well, notice I don't actually have any exponents, but I do have an x. That's technically an x to the 1st power. So degree is 1. And then this technically has 1, 2 terms. Okay. Question number 6. Again, you have an x in the denominator. So this is not going to be a polynomial. Again, this is a rational function. Okay. Question number 7 is a little tricky. Looking at this, if you wanted to find your actual polynomial, you would need to actually multiply and FOIL this out. So if I FOIL out the x minus 3, that actually, if you know your trick for perfect squares, that's x squared minus 6x plus 9. Okay, but I still actually have to multiply that by 5x. When I do that, sorry that I don't have tons of room here, that's going to be 5x to the 3rd power minus 30x squared plus 45x. Okay, looking at that now, is that a polynomial? Yes, it's a polynomial. What is the degree? The highest exponent, again, this is an x to the 3rd power, so degree is 3, and it has 1, 2, 3 terms. So you couldn't have really been able to tell at least the number of terms without FOILing it out. You could have, well, you might could have, but you could have maybe told the degree. This x is squared, so that's going to be an x squared, and then you multiply it by another x, so the highest exponent there would be an x to the 3rd power. Question number 8, sorry that this notes are looking like chaos. Question number 8, this is also not a polynomial because you can't have an x as an exponent. This is actually our exponential equation where you have like some number, we usually use 2, 5 to the x power, that's an exponential, so no, okay? So we can actually determine, the degree and the number of roots, or the type of roots, is going to help out a lot with graphing these equations. So really we were supposed to use our calculator for this, but I don't want to use the calculator because we don't have to, okay? I'm going to flip this page and we're going to take some notes on what the graphs look like, and then we'll go from there. But first, we can tell our roots or our solutions, remember, just from looking at these equations, okay? What are your solutions to question number 1? Well, this is x equals 2 and x equals negative 3. That already tells me about my graph that I know it's going to cross here at 2 and at negative 3. Okay, the same is actually true. That's a quadratic. We actually could sketch that one. You know what that looks like. But question number 10, again, what are your roots? This one's 0. And this one is 4. Okay, so just like with a quadratic, all your polynomials, your roots, are going to be your x-intercepts. So 0 and 1, 2, 3, 4. Okay. This one has a solution of 2, so x equals 2 is a x-intercept. This one has 0 and 4. So 0 and 1, 2, 3, 4. Okay. Cool. So let's flip this over and let's take a little bit more notes here, okay? On our graphs of polynomials, the first thing, and just like transformations, the first thing it really helps to know are your parent functions, okay? So I'm going to sketch a whole bunch of them up here. There is a pattern. Let's see if you can kind of catch on to it. So first of all, you already know what a positive x squared graph looks like, okay? It makes this U shape, looks like that. I'm going to draw my arrows just so you know it continues on. And you already know what a negative x squared graph looks like. It's an upside down U. You really should know what a positive x cubed graph looks like because we've already done one of those. I made that weird S shape. I'm going to kind of over exaggerate it here this time, and you'll see why here in a little bit. Notice for the positive x to the third, it starts at the bottom and then works its way up. Negative x to the third is going to start at the top and work its way down. Again, the same little S shape. Okay. X to the fourth power, okay, creates this W-looking shape. Okay. A negative x to the fourth, if you can take a guess, has an upside-down W or an M-type shape. Okay. There is a pattern here, and it's going to continue. So an x to the fifth is going to look pretty crazy. It's going to look like this. 2, 3, 4. A negative x to the fifth starts at the top and works its way down. Okay. So to be honest, there's this little rule that the degree tells you how many turns you can have in your graph, and it's going to be 1 less than the degree. So this has a degree of 2, so it's going to have 1 turn, and that's what it has. This one's a degree of 3, so it's going to have 2 turns. Degree of 4 can have 3 turns. Degree of 5 can have 5 turns. And if we wanted to get crazy and do a degree of 6, it could potentially have 5 different turns. Same thing with the negative 6. Okay. Also, notice that there's a relationship between our even powers and our odd powers. Okay, even powers are both going to end in the same direction. If it's positive, they'll both end going up. If it's negative, they'll both end going down. Okay, with the odd powers, positive, they're always going to end in opposite directions. The positive is going to go from bottom to top. The negative is going to go from top to bottom. Okay, so knowing the degree of your polynomial can tell you a lot about what the shape is going to look like. The other thing that's going to tell you a lot are your roots. Okay, so looking at this little notes, they're going to be smooth and continuous. You're not going to have any crazy turns or holes or breaks or gaps. Domain is infinite, all real numbers. The end behavior is going to be the same as the power function of the same degree. That's what we're talking about here, our end behavior. With our roots, so depending the degree of the polynomial tells you the number of possible roots. So a quadratic, for example, we know can only have 2 roots. A x to the third could have 3 and x to the fourth could have 4. Okay, so the degree tells you how many roots. And the type of root tells you a lot about the graph. At a single root, this is just going to cross the x-axis. And you know what that looks like, right? It's just gonna cross the x-axis. Those would both be single roots. Okay? At a double root, we call it bounce. Bounce. So what does that look like? It's going to hit the x-axis and then it's going to bounce. That's what a double root looks like. Okay? A triple root, we say it changes concavity. So this is kind of a crazy word, but you've actually seen this before too. That's whenever we do our parent cube function and it does this weird, it's curved one way and then it's curved the other way, that's it changing concavity, okay? That's because whenever we graphed our perfect x cubes, those were all technically triple roots. They all changed concavity at that point. Okay, so just knowing this, I can tell you a lot about how to graph these equations. So flipping back to the front of this, okay, question number 9, we know that this is an x squared graph. We know it's positive, so we know it kind of needs to be shaped like this, okay? Both of my roots are just single roots, so it's going to cross the x-axis at those 2 points. Crosses, crosses, and I've just sketched that graph, okay? Question number 10, looking at this, the degree of this polynomial, if you FOILed this completely out, that would be a positive x to the third. So I know it kind of needs to look like this, okay? The x to the 0 is a single root, so it is going to cross the graph at x equals 0, but x equals 4 is a double root, so it is going to bounce at 4. So it looks like this. Crosses at 0 and bounces at 4. So that's exactly what I'm going to do. I'm going to start down here. I'm going to cross at 0. I'm going to come back down and I'm going to bounce at 4. Okay? Notice whenever it said we were sketching these graphs, it says with no y scale. So this is not to scale at all. We actually, right now, you don't know enough to figure out how high that's going to go and stuff like that. So that's why these are very sketched. But we can perfectly graph what it's going to do around the roots. Okay? Question number 11, this is a negative x to the third graph, so I know it's going to kind of look like this, and x equals 2 is going to be a triple root, right, because it's cubed, okay? X to the fourth was a double here because it's squared. That means there's technically 2 of them. So this one's cubed. That means it's going to change concavity at 2. And again, this is a graph that we could have done even before this lesson, hopefully, if you remembered your parent functions. It's going to start at the top, it curves one way, and then it curves the other way because it's changing concavity, okay? Number 12, these are both, this is a x to the 4th power, a negative x to the 4th power, so I know it's going to make that M shape, okay? And these are both double roots because they're both squared, double roots. So that means it's going to bounce at both 0 and 4. Looks like this. So I have to start down here. I have to bounce at 0. I have to come back and bounce at 4. Okay, let's do just a couple more. We have a couple more here in our notes. Question number 13. Again, you have your roots here. X equals 0, x equals 1, x equals negative 4. So that's the first thing I'm going to do. 0, 1, negative 1, 2, 3, 4. Okay, if I FOILed this out, if I multiplied this out, this would be a positive x to the third graph. So I know it needs to look like this. All of those roots are single roots. That tells me it's going to cross at each one. So cross, cross, cross. Okay. We're going to change the game here just a little bit. Notice this equation is not factored out. So that's the very first thing you're going to have to do, is find your roots or your solutions. Okay, I can already tell you that this is a positive x to the third graph, so it's going to kind of look like this. Step 1, let's factor this. So always check for a greatest common factor first. I could take the x out. That leaves me with x squared minus 4x plus 4. Now I can factor this. That's going to be a minus minus. What multiplies to be 4 and adds to be 4? 2 and 2. With the common factor of x in front. So my solutions here, x equals 0 and x equals 2. Technically there are 2 x equals 2. So that tells me 2 is going to be a double root. 0 is a single. So here we go. 0 and 2. It's going to cross at 0, bounce at 2, and it looks like this. So that's what I'm going to do. Cross at 0, bounce at 2, and then it continues on up through the work I just drew there. Okay. Let's do another one. Question number 15. This is a fun one, okay? It's a negative x to the 4th, so I kind of know it needs to shape like this. Okay. Step 1 is factor. I can take a negative x cubed out of that graph, that equation. That leaves me with an x plus 3 if you factored out a negative x cubed. That gives me my two solutions are 0 and a negative 3. Now again, because this one is cubed, that means that that is a triple root. Okay, so my solution 0 and negative 1, 2, 3. Okay. It is going to cross at negative 3 and change concavity at 0. So this one, check this out, you're not really going to like it very much. It only kind of looks like this. Okay, it's going to start at the bottom, cross at 0, and cross at negative 3, and then on the way back down to 0, it's going to change concavity. So it curves one way, and then it curves the other way. So I kind of like to call this one, it's like a lazy M. This is technically the other side of your M, it's just really weak. Okay, but you can definitely see that it's changing concavity here, crosses at negative 3, and kind of looks like this. All right, one more graph. This one's a positive x to the 4th. So that tells me it's going to look like this. Okay, factoring it out, step 1 is I can factor out an x squared. That leaves me with x squared minus x minus 20. Factoring that, that's going to be a minus and a plus. What multiplies to be 20 and subtracts to be 1, 5, and 4. That gives me my solutions are 0, 5, and negative 4. Okay, so 0, 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay. 0 is actually going to be doubled here because, again, notice that this is an x squared. Okay, so a double root at 0, single root at 5 and negative 4 looks like this. That tells me it's going to cross, bounce, cross. So that's what I'm going to do. Crosses, bounces, crosses. Okay. And that's how you sketch polynomials.